Greetings. The Pfizer Colloquium. So, welcome to the 30th Annual Distinguished Statistician Colloquium, sponsored by Pfizer, ASA, and UConn. Today, we honor the distinguished career of Dr. Nancy Reid. First, we have some important safety announcements. Welcome to the Conover Auditorium at the DOTS Research Center. In case of an emergency or fire, there are two exits, the main entrance and the front exit off the stage to your right behind the podium. Please note the nearest exit to your seat. Remember, no smoking is allowed in the room or in the building. Please be aware that this program is being filmed and live streamed. We recommend you confirm that your mobile phone is silenced. Now that we have covered the important safety information, let's move on to our exciting program for the afternoon. But before that, I forgot to mention the restrooms are on the right side all the way from the hallway. And we'll have a break at some point after the first part is over. Now I invite Dr. Ofer Harrell, the Dean of the College of Liberal Arts and Sciences, to share about the history of this series. Ofer.
Thank you, Deepak. Can you hear me now? Okay, good. So good afternoon, everyone, and welcome to the 30th Pfizer Distinguished Statistician Colloquium here at the University of Connecticut. I'm Ofer Harrell, the Dean of the College of Liberal Arts and Sciences, and I happen to be a statistician as well. Now it's on the side, but that's what brought me here. So between us, for me, this is one of the most interesting speaking engagements that I have on my calendar, probably for the whole semester. We are lucky that this event is on a special day. Today is Rosh Hashanah. For Jewish people, it's the New Year. So we are starting the year on the right foot with an excellent speaker, and that's going to be a great footing for the coming year. This event has a long and proud history, dating back to the 1978, under the leadership of UConn professor Harry Poston and David Salzberg from Pfizer Global Research and Development. Their vision was to create space where statisticians from academia and industry could come together, exchange ideas, and advance the field. Over the years, the colloquium has generously supported by Pfizer, the UConn Department of Statistics, and the American Statistical Association. This event continues to thrive thanks to the dedication of steering committee, which include Joe Capillari for Pfizer, well, I was told to point to you.
Okay, I'll take the credit.
Okay. Our own professor Deepak Day and Ron Wasserstein from the ASA. We owe them a great deal of thanks for keeping this important tradition alive. We are also very grateful for the Pfizer continued commitment to collaboration among academia, industry, and the broader statistical community. Today, we have the honor of welcoming truly distinguished statistician, Dr. Nancy Reid of the University of Toronto. Dr. Reid's contribution to statistical theory, likelihood inference, and design of study have been transformative in academic circles and public policy application. Her leadership has been recognized globally with honors that include fellowships in the Royal Society and the National Academy of Science, and most recently the David R. Cox Foundation's of Statistics Award. I was lucky to get a very short time with Nancy on the National Academy Committee on Applied and Theoretical Statistics, which is a lot of fun committee for me. So in her talk titled When Likelihood Goes Wrong, Professor Reid will explore the challenges and nuances of likelihood inference, a topic at heart of much of her pioneering work. Please join me. and welcoming Professor Nancy Reid.
I'll just use this one.
I'll give a brief introduction again. So, again, let's invite Nancy, and I just add few more things in addition what Ofer mentioned, that her research includes a lot of huge branch of areas of statistical theory, likelihood inference, design of studies, and statistical science in public policy. She graduated from Waterloo B.Math in 1974, and then University of British Columbia MSc 1976, Stanford University PhD 1979, and Imperial College London in 1980 for a postdoctoral fellow under Sir David Cox. She joined University of Toronto in 1986 from the University of British Columbia. Nancy is a fellow of many associations, but he mentioned mostly the Royal Society, the big things outside statistics community. But she is also a fellow of American Statistical Association, IMS, Institute of Mathematical Statistics, and so on and so forth. So foundation of statistics is the foundation of her work, and today's title is quite famous.
It's missing. But
Missing
I'll
is
get
the
it for you.
title,
Don't
yeah.
worry, it's
So she
coming.
will mention
It's
the title.
coming.
Okay.
Okay.
Nice.
Thank you, Deepak.
Yes.
Thank you. Okay, so I apologize to people who are at JSM this year in Portland. Well, I'm not sorry for you, it was a lovely meeting, but I did give much of the similar material at that talk, so you might be seeing it for the second time. But I still don't understand it after going through it hundreds of times, so I guess that's all right. I was at UConn for one of these meetings a million years ago. Actually, I know exactly how many years ago. It was 31. And I date that from when our children were born, with Peter McCullough and David Cox, of course. It was great fun, but in this picture, I think we all look extremely nervous. And we were actually extremely nervous because it was very unusual. It's hard to imagine now, in those days, to videotape a lecture. And so, you know, these old photographs, the black and white or sepia photographs, people look so scared because it cost a fortune to take their photographs, so they were paralyzed with the unusualness of it. That's how we felt in the video presentation. I wanted to mention David Salzberg's book, The Lady Tasting Tea. I've used it quite often in my teaching and research. And actually, right at the beginning of his book, in the preface, he says, by the end of the 20th century, almost all of science had shifted to using statistical models. So that was like, I don't know, 24 years ago. And it's only accelerated since then, right? And my talk is about statistical models, so I thought that was an apt quotation from someone very influential at Pfizer. I won't spend time on the outline. We don't have so much time, and you can follow along. But I'm going to start with just a totally haphazard collection of things that I thought were interesting when I came across them. And in each, there's 4 of them, and in each of them there's a scientific problem and a statistical model that's been addressed to help with that scientific problem, kind of supporting David's observation that it's everywhere. The first one is about wine. I like to drink wine, and this particular paper asked the scientific question, can historical records of wine quality be used as temperature proxies? Because even in Europe, and especially in France, I suppose, even if they don't have very good climate records, they know exactly what years were good for wine, right? They have very good records of wine quality. This is, of course, observational data, and they describe in the methods section, which is the section I always turn to, we used a statistical linear regression model for wine quality based on a local temperature and precipitation. Of course, I don't have time or the expertise to go into these examples in detail, but roughly speaking, they concluded that if you were very careful about where the data came from, that this could be a useful adjunct to study climate change. The next example comes from social sciences, and it's a really interesting randomized trial on the effects of investigating the effects of a guaranteed income. So the scientific question was, does a guaranteed income supplement affect various labor market measures? This is written by economists, and it's an NBER working paper. This was a randomized controlled trial, and people were randomized to either receive $50 a month or $1,000 a month for a period of 3 years. And the people in the study were all lower income, and so the $1,000 a month was a substantial increase in their annual income. So the question is, what do they do with it? Do they use that extra comfort to party, or do they use it to go out and find a better job, or to upskill, or to somehow make their labor marketability improved, which is what the economists were curious about. And they used a statistical model that we would see in any study of causal inference, and the hoped for cause is the income supplement, that's the treatment, and there's a great number of covariates that have to be selected for and modeled and so on. But again, it's a pretty straightforward linear regression model. The picture kind of shows the outcome in a way. You probably almost certainly can't read the small print, but the one to the left, so minutes per day went down on what they call market work. So actually people worked less when they had the extra income. And social leisure minutes went up. And so you can imagine in such a polarized climate, the raging debate about a guaranteed income, whether it makes you lazy or whether it makes you better accommodated to society, right? And they came down rather carefully on both sides of the debate, pointing out that these effects occurred, but also pointing out that if that's what people choose to spend their time/money on, then perhaps that's good all around in creating a more equal society. This one, I studied this problem years and years ago and didn't know how to deal with it. So I was interested to see this, and it came from a group at the University of Toronto this summer. So the question is, women who have cancer in one breast sometimes elect to have bilateral mastectomy. And the question is, does that improve survival? It certainly improves recurrence because it can't then recur in the other breast. But the question they were asking was, does the bilateral mastectomy improve 20-year survival? And they have a very large database, and they created a case cohort matched set to study this problem. And they found that it actually didn't improve the survival rate or reduce the risk of death over 20 years, which I think they thought was a bit surprising. I haven't put a statistical model, but you would recognize Kaplan-Meier method as a standard survival data method, and that was also used with the Cox's proportional hazards regression. Sorry. And the last example is from the physical sciences. This is a question of a problem that arose in astronomy, and an astronomer Eileen Meyer is her name, got in touch with me, and I worked with my former PhD student Yanbo Tang on this problem, which was they had very good observations from the Chandra Observatory of various X-ray jets, and their question was, are they consistent with the current theory? In this case, it was a little bit easier to have a somewhat plausible model, or I guess a scientifically motivated model, because they're counting things, and so for counting things we use the Poisson distribution. And the question was simply, did the background and source counts, were they consistent with this model with no additional source? And the scientific conclusion was that it wasn't, which is why the paper was published. They felt that the variability that they see is not really compatible with the current theory, which is always interesting for a scientist, of course. Okay, extremely haphazard, a bunch of models, a bunch of parameters. So now I just want to talk about where do they come from. We don't often stop to think about this, or at least I didn't. I'm used to lecturing to students and saying, okay, we're going to use this model to analyze this data, and we don't spend a lot of time thinking about what all the pieces mean. But why did they use those models? Well, quite often it's because that's what everyone else who publishes in that field uses. So that's maybe in the income example that would apply. Sometimes it's what the lab's been doing for years and years and years, and they're not about to change, and that's true of the breast cancer. They've published maybe 20-some papers based on more or less the same cohort, and they often use the same methods. In applied statistics, we kind of drift, at least I do, drift to a kind of prescription. If the response is binary, then logistic regression is a good place to start. If the response is a time to event, then maybe the proportional hazards model is a good place to start. If there's repeated measures over time, we should look at some of the models for time series and so on, or maybe a random effects model. And very rarely, I would say, they might be motivated by an actual theory. The X-ray jets is motivated by a sort of physical theory of how these jets of stuff emerging from stars gets tossed out, and then we get to observe it. The economists have lots of theories about how the economy works, and so their models are often motivated by that. My go-tos for thinking about modeling are the Statistical Models book by Anthony Davison, who emphasizes that the key feature of a statistical model, rather than some other type of model in another discipline, is that we need variability because our data is variable, and that probability is a very natural way to model that. And this kind of wisdom you don't find everywhere, but he's noting that the art of modeling lies in finding a balance that enables questions at hand to be answered or new ones to be posed. My other go-to is a wonderful book on applied statistics by Cox and Donnelly, emphasizing that probability models are to aid us in the interpretation of data and not the other way around. Like the data doesn't say, or the application doesn't say you must use this model because that's what everybody uses. The model has to help us understand what the data is trying to say, I guess, is a paraphrase of perhaps what they were saying. And noting that there's kind of two kinds of randomness that we have to think about. There's maybe more than two, but two main ones. There's lots of perturbations that are not of any interest in themselves, but they distort our measurements. And then there's variability in the phenomenon that we need to understand. So there's kind of two ways of thinking about how you'll bring probability into a model. There's some lovely papers as well in statistical science where, in particular, there's a contrast in Lehman's paper on model specification on the difference between empirical and predictive models contrasted with explanatory models. Now that's really I think we're quite accustomed to that in the new world of machine learning, because if we want to kind of hold our own, I guess, in machine learning, we say, yeah, but we're not always interested in prediction. We'd like to explain what's going on, and you guys just want to predict what's going to happen next, and so we can all work together on these kind of two arms. But these papers were written in 1990 when machine learning barely existed, so I thought that was interesting. And there's also, of course, the book also called Statistical Models by David Friedman. His is slightly more negative. He was showing the lack of connection between models and the real phenomena. So that's the models, but then these models are very likely to be parameterized, so we have a class of models, and the parameters might be finite or infinite dimensional, of course. And hopefully one or more of the parameters is kind of encapsulating the key aspects that we'd like to know about for the application that we're looking at. And we very often need many other parameters to complete this specification, and the meaning varies, of course, always with the application. So one of the key features of statistical work as opposed to other mathematical work is that we're always kind of the back and forth between the application and the practice. Even when you're doing foundations, I think it's very important to keep in mind that interplay. This sounds a lot simpler than it is, I would say. If I've learned anything over the many years, I think it's a difficult problem. And one of the most difficult papers you'll read on this topic is by Peter McCullough, What is a Statistical Model? But I was surprised and to be reminded, if I ever recognized it, in the Pfizer interview that I had the snapshot from, he was starting to think this through already, and he asked David a question exactly about it. He said something like, is a parameter just a Greek letter in a formula, or does it have some intrinsic meaning that carries on more deeply? And I think this paper is his attempt to answer that question. Again, David Salzberg mentions along the way probability theory alone is insufficient to describe statistical methods. Okay, so we have, let's say we have a model or a class of models, or we have something we're reasonably comfortable to start working with. Where does likelihood have to do with it? This is what I've spent almost my whole career on, is likelihood. So what's the important part there? Well, one way that I think about it is that likelihood just forces you to think about the model, because it takes a probability density function, which you learn in second-year probability. There's a whole lot of them, and you have to figure out how to integrate them and so on. And it turns the question around, and it says, don't think about this parameter will generate this certain type of data. We've got the data. What parameters might have generated that data? So it forces you to think backwards. I said inverse problem. These gray things down the side are reminders to me. Brad Efron was the first person I heard describe this as an inverse problem, when a very eminent physicist said to him, what's the difference between statistics and probability? And I was shocked that this eminent physicist didn't know the difference between statistics and probability. And Brad said, well, statistics is the inverse problem. And the physicist said, oh yeah, right, okay, done. So I think that's a nice way to think about it. It also provides a very convenient way to compare different parameter values, and there's usually a few parameter values that have a special meaning in the context of the application, so we can compare them by taking the likelihood ratio. It provides a kind of summary of it, so you can't draw this summary in very many parameter dimensions, so I've picked only one parameter dimension to draw, not the likelihood function, but the log likelihood function, because it has a nicer shape. And I've actually standardized it so it has its maximum at 0. So I've really plotted the log likelihood function, the log of the capital L, minus its value at the maximum. And this looks, there's not that many applications, and none of those 4 scientific applications that I set out, where you could easily extract enough data from the paper to draw such a simple likelihood function. But there was a great Pfizer paper where there was, and that was their first paper on the vaccine for COVID-19, in which it was really a 2-arm trial with some hundreds of thousands of people in each arm. And in the vaccine arm, there were 8 cases of COVID, and in the non-vaccine arm, there were 162 cases of COVID. And was our first emphasis that it worked. And this is the binomial likelihood from that data. But in general, we might think of just a sort of generic likelihood function. And one of the other things, in addition to comparing parameter values, we can get some summary measures. And that's what we usually work with, right? The maximum likelihood estimator, or the point where it's maximized, or the comparison, as I mentioned before, of 2 different values. And the other key feature that plays a role is the curvature at the maximum, which tells us how precise our estimate of the maximum is in some sense, because it shows us in a certain way how much information there is in the data about the parameter. And I've put down at the bottom where it might even fade away, but it could, if you have a prior, it can be converted to a probability distribution, but it's not a probability unless you inject that into the problem. Okay, so this slide has a lot of notation, but I just wanted to remind you where those summary statistics, why those summary statistics are useful. And I'll try not to spend too long on this so we have time for the later work. So if we have independent observations, then we know that the joint density is a product. So the likelihood function is a product, and so the log likelihood function is a sum. And whenever a probabilist sees a sum, well, then we have central limit theorem, hopefully. And in fact, that's exactly what we do have. So we would most likely find the most likely value of the parameter. And we often find that by solving an equation. So we want to maximize a function. We take its first derivative and set it to 0. And that function, the first derivative function, that's a sum because the log likelihood is a sum. So that's where we use the central limit theorem. And if we're going to use the central limit theorem, we need its variance, and we know what it is. And then we also have that curvature, how tight or flat the likelihood is. That's going to tell us how accurate our inference is, and that tightness is related directly to the variance of the thing we're working with. So the central limit theorem plus the curvature gives us essentially our answer. Okay, so our answer then is, from the central limit theorem, the score is approximately normal, the MLE is approximately normal, and the drop is approximately chi-squared. Okay, that's a refresher course for those of you who haven't seen this for a while, and familiarizing with my notation if you have seen it recently. But too much notation. The things to remember are there's a central limit theorem, and then there's an approximation that we derive from that. And so when will that work and when will that not work? Well, it won't work if there's no central limit theorem. And so if we're not averaging a bunch of stuff together, it's not going to work. So for extreme values, it won't work. Or for change points, it won't work, right? Because then we won't be averaging enough things together. A change point is a change, so the only information you get about it is when it changes. That's not too much information. An extreme value is very rare, so you're not going to be aggregating information about that. So that's kind of a guideline to where the regularity conditions might fail. But a more practical way to look at it, if the picture seems a bit cluttered and the notation seems a bit confusing, you're using this all the time because that's what's built into R or Python or whatever software you're using, or SAS. This is some R code. There's all the estimates, theta 1, theta 2, theta 3, theta 4, and so on. Those are the hats. And the standard error is from the inverse at the hat. And the p-values are from pretending that's normal. So that it's something that we use every day. And the drop is the deviance, analysis of deviance is the drop. So from a more practical point of view, this is something that's built into every statistician's workday, more or less. It's a little bit too simple. I've presented it as if we were interested in a whole parameter, p-dimensional or one-dimensional, but even in this little model, there's 5 parameters. So where did that come from? It just came from the diagonal. This would be a 5 vector, and then there would be 5 diagonal entries, and those would be the variances. So in another way, you could say it came from the profile likelihood that we identified, say, theta 1, the coefficient for age, was of interest, and we decided that all the others were not of interest for line 1, and we used the profile where we just maximize out the nuisance parameters. And that's where it can also go wrong, because if there's lots and lots and lots of nuisance parameters, that maximization concentrates the likelihood too much. So lots of parameters, we can have things go wrong, even if there's many parameters relative to the sample size. So my first version is P is comparable in size to N. And you know that if, for example, even in least squares, if you would, the residual variance needs to be divided by N minus P, right? Not N. It'll be too small if you divide it by N. You have to adjust for the fact that you estimated all those coefficients. And the maximum likelihood method doesn't know that. So if you just did what I just described on the previous slides, you get the wrong answer, but then you stop and look and think, oh no, that's the wrong answer, we have to fix it. And of course, Fisher saw that in Bartlett and so on 100 years ago. But that's a simple example where if you have a lot of parameters, the profiling step can be quite poor. Now we're interested in more complicated relationships between parameters and sample sizes. We might have so many features that they grow with the sample size. So every time the sample size increases, we get more features. And that could go faster than the sample size or slower or somewhere in between. So there's a lot of kind of new asymptotics being developed in this regime. But even in this regime, you need to do something to fix it. Other things that can go wrong, you can have, well, I said weird, I just mean a parameter space with not open sets, not a simple topology for the parameter space. The most simple example, one of them is a mixture model. It's not a weird parameter space, but if P is 0, then there's no mixture, so there's no theta 1 and theta 2, there's just a theta. So you can't really identify all three parameters in certain settings. Another example is a boundary value for variance, right? You can't let a variance estimate be less than 0, but if you have several components of variance, some of your estimates might be 0 exactly. More often nowadays is computational intractability, where we might model a lot of latent factors or hidden variables if you're in machine learning that have their own distribution, so the likelihood function just isn't computable and we have to work with something a bit simpler. Another is that we just might have got the model wrong, right? The true model might be something not in our collection of models at all. Like we're using this collection F of y theta, and theta's in some parameter space, weird or not, but maybe we're wrong. It's not normal, it's T or something, or it's just not nested within the normal. The T is slightly nested, so that's a poor example, but I'm sure you've seen examples like this. And I'll just mention in passing, as I said before, likelihood's not a probability, and that's the picture that I sent when Juliet asked me to send some picture that describes my research. I used this picture in the last talk I gave here, so I wasn't going to spend much time on it, but I put it here momentarily. The red lines are posterior distribution from a flat prior for a particular summary parameter, and the blue lines are the p-value functions for the same problem, and the p-value functions are correct in repeated sampling, but the posterior survivor value functions are incorrect in the sampling, and that's because the prior that was used was not suitable for this particular problem, but it's kind of because likelihood isn't really a probability. So, okay, but I wanted to spend the rest of the time that I have on the misspecification, and that leads to some recent work that I did with Heather, who's here for the discussion later, of course. Who's keeping track of time? Deepak probably is, and the students are. And you're telling me I have 2 minutes left? No, 20 minutes left. Okay, thank you. Okay, 20 minutes I can handle. 2 minutes I'd have to go through all my slides really, really, really fast. Okay, so one approach to misspecification, what you might call a classical approach, because Cox developed it in the 60s. We have a true model and a fitted model, and we use the fitted model to get our estimate. What happens to the limit theory? Like, I'm not IID sampling under the model anymore, so all those central limit theorem stuff and everything isn't going to be very useful. But you can show that theta hat converges to something in it under some smoothness and so on. And it converges to the least wrong value of theta. That is the one in the class we're fitting that gets you as close as you can to the true model in some sense. And the some sense is the KL divergence. So we're minimizing some kind of discrepancy between the true model and the model that we're using. And that with enough data, our estimate will converge to that value. And you can even show with enough regularity that there's an asymptotic normal distribution there. course, you can't have the variance that you had before because we're in a wrong model setting, so you need a different expression for the variance, which the details are given here. This is what most people know as the sandwich estimate of variance, because there's two things the same on the outside, j's, and an I inverse on the inside. And one is a variance and one is a mean. And so those have to be estimated, of course. I won't go into that particularly, but once we have those estimates, then we have an estimate of the asymptotic variance. And so these are the two versions of information that I had before. One was the red bit, that was the curvature, and the other was its expected value. This is slightly, these are all computed now under the true model, so that's a little bit harder to think about. But, so we can do that, and we can just say, okay, well, instead of making inference about the true model M, we'll make inference about this parameter, whatever it is, the one that's closest to the true model, and we can just kind of proceed more or less as usual. And you'll often read in at least two of those 4 papers that I mentioned at the beginning, somewhere buried in the methods section is like a sentence that says, we used a robust estimate of variance. And what they mean is they used the sandwich estimator of variance because they weren't exactly sure that their model was well specified. Another thing you could do that I worked on over the years is something like a more flexible inference function. Instead of using the likelihood function, maybe we could use something else. So in this case, my true model is actually a parametric model. Now my observation, each independent observation is a vector. And so that might be kind of a complicated model to fit. And one way to do it is to specify some subsets and just fit a simpler likelihood. It's better to see an example. So this is called pairwise likelihood. So instead of fitting the product of all those d-dimensional f's, we just take observations in pairs and fit the model that way. We might take the observations in sequence and pretend that they're AR, autoregressive of order only 1, instead of the full dependence that might be in the whole vector. We might just say, okay, we'll ignore all the higher order dependence and pretend it's Markov. Once you start working with this, you quickly realize that the theta might not always mean the same thing, depending on where you started from. This theta belongs to a d-dimensional density, and then this theta belongs to a 2-dimensional density, so are they going to be the same or not? Well, if it's an entry of a covariance matrix, yes, they'll be okay. Even the entry of a mean vector, they'll be okay. But for other models, it might not be quite so straightforward. So we're back to asking Peter's question, is a parameter just a Greek letter in a model, or does it have some other meaning? These are also examples of, or were motivated by the pseudo-likelihood that BSAG proposed in 1974 that if you work in spatial data, you probably will have used. Another way to do more flexible inference functions is just to look at maybe some, not specifying a whole distribution, but just a mean and a variance. And that's where generalized estimating equations come from. Don't worry about the formulas. They're either familiar or they're not, but the essential part is that we're modeling the expected value, we're modeling the variance, and not anything else. We're not modeling the whole density. There's a very neat way to do this with, so that gives you an estimating equation, but it doesn't give you an inference function. But the quadratic inference functions that were proposed by Q et al. Is kind of an interesting approach to creating an inference function from this specification, which is kind of neat. And there's some recent work by Emily Hector from NC State that has a kind of unique take on this I thought was quite interesting. So another thing we might do is just make the models more flexible. So we'll identify our parameters of interest and make everything else just quite vague. The most famous is proportional hazards regression. So the regression is going to be e to the x beta, as we're familiar with. But the hazard for the underlying hazard function, that's going to be just some arbitrary function. So it's a semi-parametric model. There's lots of these. Empirical likelihood is another version. And semi-parametric regression is maybe another version. We're particularly interested in the treatment and not so much in the covariates. This is somehow really popular right now, right? We fit this covariate function with some kind of deep neural network or something, and then we isolate the parameter of interest and its effect on the response, and we ascribe that to the treatment. Yeah. And so again, does the parameter have a stable interpretation over all those different types of models? That is, does the theta or the beta or the psi, are they meaningful no matter what the omega or the t or the h are? I guess is a question that has to be answered, and that's an assumption of the model. So the way I've set out these models, the answer is yes. But in general, you might wonder when the answer is yes. And one approach to this was studied by Van Steeland and Dukes. And this third model, this semi-parametric regression model that I mentioned, that this comes from their paper. And instead of working with this model, they defined instead something they'd like to estimate, called an estimand. So not exactly a parameter, but it's a weighted treatment difference. So here's the expected value of y given the treated minus the expected value of y in the untreated, conditional on all the covariates. And we're going to weight that by something related to the covariates, in this case the propensity score, the probability that you got treated given your covariates. So that's a well-defined thing. It's not necessarily psi, although it would be if this model is correct. But if this model was wrong, this would still be a well-defined thing to think about. And the question is, what methods would we have for studying the convergence of our estimators to this particular estimand? This comes up, it might look a bit familiar if you're studying causality as a kind of double robustness question. Thank you. Oh, it's also time for me to stand up. My watch is telling me. I'm standing. I should say that the paper by Van Steeland and Dukes actually used generalized linear models, but the principle is exactly the same. So what did they like about this estimand? It's meaningful if the model's misspecified. It can be estimated even if you get part of the model wrong. And if this is the correct model, you're still okay. What kinds of models might have that property or a property analogous to that? And that was a question that Heather raised in the discussion of Van Steeland and Dukes, and that led to our work, motivated originally by this particular example from a paper with Heather with David Cox. This is an exponential matched pairs, and we have survival times for n pairs, and they've been randomly assigned to treatment or control. And in this case, we're going to let every single pair have its own nuisance parameter. So we got lots of nuisance parameters here. We have n nuisance parameters and 2n observations. So we have p increasing with n. And if you use an exponential model, for example, that's a simple one, we might have the psi representing the ratio of the rates. So it's been modeled as exponential with rate lambda over psi in the control group and lambda times psi in the treatment group. And the psi never changes from group to group. That's a common effective treatment. There's many things you could do. You could try to eliminate the nuisance parameters by some conditional or marginal argument. But a very common thing to do is to model them as random effects. So let's do that. The random effects model is a gamma. And then we have an integrated likelihood, and it's not even too difficult to work out what it looks like. And it turns out that in this model, the parameter of interest is orthogonal to now the nuisance parameters are in the mixing distribution, right, the random effects, which means that the estimate is asymptotically independent of any estimates of the nuisance parameters. It's one property of orthogonality. There's a kind of separation in the information. matrix for this model. So that's kind of interesting because then it doesn't, the nuisance parameters don't influence the estimate as much. But what's more interesting is even if the random effects distribution wasn't gamma, but it was something else, you used a gamma, but you were wrong. It's still orthogonal. That is, the parameter of interest is still orthogonal to the parameters in any random effects distribution, not just the gamma. And so that means that the estimate, the maximum likelihood estimate, is consistent. It's a kind of, I don't know if it's a double robustness, but it's a robustness property that the estimate is consistent even if the random effects model is incorrect. So what makes that work? Because that was the subject of our paper. I'm going to skip the details of the calculations, but so we tried to formalize in some way what makes that thing hold. Like why do we get consistent estimate of the parameter of interest even if we misspecify other parts of the model? And so we looked at a formalization in which there's a true model which has an actual true value, which we're calling psi star, and there's a fitted model where psi has the same interpretation. So we can interpret psi either from the true model or the fitted model in the same way. And we know the maximum likelihood estimates converge to the closest value, right? We know that'll work, like they're going to converge to something that's the closest to the F in the M category, the KL divergence that I wrote down earlier. So we know that that's the convergence, but we don't want the convergence to this value psi sub M0. That is the closest psi value that you can get in the class of M, but rather we want it to converge to the true value, which we presume exists. And so when would we have that? And the first thing that we remarked was that we need a certain expectation to be 0 to get an unbiased estimating equation, and that it's kind of hard to work with because these expectations are all under this model that we don't really know what it is. And so something that turned out to be the case was that we could do the easier calculation instead of the one we needed if there was this orthogonality that I mentioned showed up in the exponential family model, the two exponential rates. There's this kind of global orthogonality, not global in the whole parameter space, but global in the sense that even if we get part of the model wrong, the estimate is still orthogonal. We call this M orthogonal because it's orthogonal in the true model, not in the model we fitted. So we have our true model, our fitted model, and if we have this M orthogonality, we'll get a consistent estimate. But M orthogonality is hard to assess because we don't know the true model. So we found some weaker conditions that would suffice. And one of them was a particular type of symmetry, and that's the one that's reflected in the exponential rates model. And the particular type of symmetry was that you kind of have a generalization of a scale model. That is, a scale model looks like f of y sigma has 1 over sigma times some base density of y over sigma. There's some kind of base model, exponential 1, and it gets shifted in this multiplicative way. In this case, we've got lots of parameters. There should be a comma here between psi and lambda, and but it's getting shifted with respect to psi as if it was a scale model, and the lambda just kind of goes along for the ride. So that generalizes to other types of groups, location groups and groups on the circle and so on. So that's one of the results that we were able to kind of study the structure of these models where we'd get the right answer even if we misspecified a good portion of our model. The other result, which I don't have on a slide, has to do with sufficient statistics, and if there's a certain linearity of the sufficient statistics, we would also get this property that would get consistent estimates. And so that's kind of for us at least, an interesting foundational observation because we have something that's kind of linking transformation models, location scale models, with exponential family models, and they're usually treated quite differently. They seem to be kind of almost at right angles to each other, but this, in a sense, ties them together. So far, we only have results on consistency. The asymptotic variance calculations are a lot trickier. I just mentioned in passing that in the matched pairs examples, the nuisance parameters could be treated as arbitrary constants and eliminated by a transformation. So if we could find what's called a marginal likelihood and get rid of them. We didn't do that. We used a mixing distribution instead, a parametric mixing distribution. And that's less efficient. It's less efficient to do the fixed, treating them as fixed constants if the model's correct. But it's that you don't have that kind of variance robustness when the model is incorrect. Thank you. Okay. There's a connection to Neyman orthogonality. If you work in machine learning, you may have come across Neyman orthogonality, which is like decorrelating the complicated part of the model from the simple part of the model through some kind of regression. And it's not exactly clear what the specific connection to it is, but it seems to be to have some relevance for problems like that. Okay, I'm going to conclude. I said I had a bunch of things that could go wrong, and I had a sort of collection of, well, things I mentioned in terms of the model misspecification. All the other stuff that could go wrong, that's the whole, like, 4 other talks, and I only have 30 seconds left now, so I can hear it ringing. I'm stopping, I promise. Just. But there's so much interesting work going on in exactly these settings. There's interesting new asymptotic theory for high-dimensional inference, for weird parameter spaces. There's lots of interesting applications of composite likelihood. And I'll remind you again that flat priors in particular can be quite influential on the posterior, and so much more. But I'm stopping there, and thank you very much for your attention.
Thank you so much for that wonderful presentation. At this time, we have time for some of your questions. So please either walk to the mic stands on either side of the podium here, or raise your hand and wait for the mic to be passed to you, and please speak into the microphone. Any questions? Not on.
Yeah, thank you, Nancy. Joe Capillari, Pfizer. That was a wonderful talk. Of the things that can go wrong, which one is most likely to go wrong? And if you had more time, what would you speak on what goes wrong?
Oh, good question. I didn't mean to do that. I meant to back up just one sec. Because there's actually more things that can go wrong that I didn't list. So I would say, well, from my personal research point of view, the first one is pretty exciting because it involves a whole lot of new math and asymptotic theory. I think from an applied point of view, this is probably one of the more worrisome ones. There's a lot of flat priors floating around out there and used in settings where it's not clear that it's not having a big influence on the answer. But maybe even going back all the way to the beginning of the talk, and I won't try to find the slide, is why are you using that model and why are you using that parameterization of that model, I think maybe doesn't get as much thought as it might need, and in the context of the application. And it's very often the case, and even when you talk to scientists who work in another field, that they'll just say, well, we have to do it this way. Everybody does it this way. We won't get published if we don't do it like this, or something like that. Or the FDA says we have to do it this way, or something like that. So I think that kind of using the model parameter as a recipe is maybe the more serious more serious than the ones in my list, maybe.
Other questions? Yes.
Hello, I'm Paul Sislo from Pfizer. Can you comment a little bit more about not when you have difficulty with the likelihood surface being like having local maxima or difficult where your normal Newton Raphson approximation doesn't lead to the right answer? Do you have, can you comment on that?
I'm not sure what to say about that, but you're right, especially in these very high-dimensional models, the likelihood surface might look like more like Switzerland than like my nice, smooth, rounded hill, right? And some solutions seem to be, well, start at different points and then see if you get to the same point in the end. Other solutions seem to be, well, you'll get a bunch of different answers, average them all together. That's another approach. And there is a little bit of work, and I haven't kept up with the literature, but Martin Wainwright and Mike Jordan had an interesting result about 10 years ago that the optimization error was actually smaller than the statistical noise in certain settings, so that even if you were getting not to the peak, but you were within reason, the noise in the data was so large it wouldn't really matter. But it seems that it almost has to be problem specific, and I don't know that there's a single right answer, or I don't know what it is if there is one.
So Nancy, you talk about this model misspecification. If I understand correctly, you're saying that the consistency of this parameter of interest does not really depend on correctly specified models if you have this M orthogonality, right? So in that case, can you share some insights on how you should specify the model in terms of which specification will give you the perhaps smallest variance, or I don't know, these two the best estimator, because it doesn't affect your consistency, right? So
Right.
what exactly is the consequence of misspecification?
The efficiency, I guess, will be the consequence, and that's a really good suggestion for further research, right? Because we don't know too much about how to relate the misspecification to the variance. I mean, it's a really interesting question of whether there might be a class of models, for example, that would lead you to nearly efficient estimators. I guess that's a little bit what the double robustness tries to address, but I don't know the answer, but it's a really interesting question. Thank you.
All right, I don't see any other hands. Any other? Oh, one more hand.
So Nancy, in today's world, we are hearing more and more often in real practical situations, people are moving away from statistical models. I don't know if that you're doing it because they see problems, but it could be for a variety of reasons. But is a model-free data analysis somewhere in our near future?
No.
Thank God, right?
I know, I see these papers that say model-free, but they're not really. Somewhere, I mean, there's some flexibility and so on, but very often some equally important assumption has to be made. I guess one example would be sparsity. You can say that you're not fitting any model, but then you're assuming that 3/4 of the betas are 0, so it's a model in a different guise. I don't see how to get away from probability models, really. I mean, it's a bit old school now, but smooth regression, even function. Well, I won't talk about functional data analysis. I don't know enough about it, but smooth semi-parametric regression. So we just fit a smooth model, But that smooth model gets parameterized, right? It gets parameterized as a bunch of smooth functions with coefficients. So there is a model, and it's a particular one. So no, I don't see a model-free future.
Nancy, a quick question. First, wonderful talk. Like I said before, as usual,
Thank you.
so many good things. In a pragmatic sense, all models are incorrect to begin with. So we are all making mistakes. So when you say what can go wrong, I think many things can go wrong. Actually, everything can go wrong.
Right.
So my question is this: are we going to an area where we can over massage model slash parameters slash efficiency, whatever else that comes with it?
Right. That's really a nice way to phrase it, because you're right. They're all approximations to some reality, or not even, but they somehow encapsulate. Gosh, I'd go back to the classics for that one. They encapsulate some aspect of a system that's of particular interest. And you're right, getting extremely precise answers within that classification might not be so relevant for practice. This is a discussion I had with David quite often about higher order asymptotics, and getting a really highly accurate answer to the wrong question is not that useful. And I would just say, yeah, but it's so much fun. But so there's some kind of well, there's a lot to think about in terms of relating it back to applications and finding what is a statistical model. Peter said it as well as anyone. What does the parameter mean in some sense? And I think that's probably more important than the very careful analysis we do later. Yeah, I would agree with you there.
I'll make one comment, Nancy. Yeah, one of the question I have, which is really a comment, and I wanted to get your feeling, that when the likelihood is not a probability in that perspective, direction, and overall modeling, because as many people may do, none of the thing could be correct, the model could be incorrect. But there are quite a few models which can be represented, there is a background model, like process model, like in many genetic experiments, and then many physical experiments, physical science, and quite often, and solving differential equation model, partial difference. So that process model and then statistical model, if they are close by, and which is covered in uncertainty quantification quite a bit. And in that perspective, we know none of the correct, but how close approximation to the process model, which is governed by nature or some physical or economical or any kind of a biological process.
Yes, yeah, no, that's a really interesting comment, and exactly, like there are a whole range of sciences where we do know how the model evolves. It's just really, really, really complicated, like the climate, for example. So we use some statistical proxies, but yeah, this new emphasis on uncertainty quantification, new for us, not new for applied mathematicians, is quite an interesting overlap between process models and statistical models. Yeah, thanks. I think that's really interesting and important work.
All right, great. Thank you so much, Nancy, or Dr. Reid. We have, okay, thank you. We have an important message from our, ooh, that's okay. Actually, we're going to move to our computer. Oops, let me get here. There we go. So here we are pleased to present a warm message of congratulations from the Executive Director of the American Statistical Association, from Dr. Ron Wasserstein. So I don't know if you can see it better from here or here, but
Hey, Nancy. I'm truly sorry that an ASA obligation is keeping me away from your presentation and this recognition today, but it's an obligation I'm sure you would approve of, a convening of statisticians and climate scientists to work on important problems. All of us at the American Statistical Association are delighted that you are the 30th Distinguished Statistician honoree. Your name fits right in with the illustrious honorees over the many years this colloquium has taken place. In addition to your prodigious talent as a researcher and your gift of being an effective communicator, what stands out to me is your grace and kindness. I am grateful for the support you have given me over the years. You are a remarkable ambassador of our profession. Congratulations, Nancy. Thank you for all you do and have done for our community. And thank you to all those at UConn and Pfizer who have made this event possible.
thanks to Ron for sending that. We're grateful for the long-standing support of Ron and the ASA. Now we have someone else who would like to share some words of congratulations on behalf of Pfizer. I invite Dr. Joseph Capilleri to the stage.
Can you put the other picture? Welcome.
Actually, we have,
Yeah.
that's this one. Thank you.
Thank you, Elizabeth. Hi, everyone. Nice to see you all. As a proud Pfizer employee of 28 years, an elected fellow of the American Statistical Association for the past 13 years, and a privileged adjunct faculty member at the University of Connecticut for 21 years, this weekend I will be grading exams. I am humbled and honored to offer warmest and heartfelt congratulations to Nancy Reid for being celebrated at the 30th Distinguished Statistician Colloquium, sponsored by Pfizer, ASA, and UConn. I would like to acknowledge the generous support and commitment of my wonderful Pfizer colleagues, Demisi Alamayu and Canon Natarajan, for their leadership in helping to make this glorious event a reality. They did the work, and as you heard, I get my name credited to the steering committee. What a country, only in America. Recently, I communicated with Haim Bar and Naiti Ting, faculty members at the University of Connecticut, on a tribute manuscript on a conversation with Dr. David S. Salzberg, where David's visit to Pfizer in Groton, Connecticut in 2017 was highlighted during his seminar luncheon with Pfizer statisticians. The 93-year-old David Salzberg is the first statistician hired by Pfizer and its first elected fellow of the ASA, and also the first to earn a PhD in statistics from the University of Connecticut. David became an ASA fellow in 1978. It was not until 24 years later that Pfizer enjoyed its second fellow in Demisi Alamayu in 2002. And Neil, you became a fellow in the year right after that, 2003, Neil Thomas. Nice to see you. Now for our esteemed and distinguished honoree, Nancy. Nancy Reid has been a patron of the colloquium for over the years. She's been present here multiple times. I've had the pleasure of having dinner with her. And her presence seems to light up the UConn faculty with much respect and admiration for her talents, professionalism, and warmth. I'd like to give a paraphrase, something I gotten from the website about Nancy's journey at Stanford. Rupert Murdoch was her was Brad Efron's advisor. He was a very kind man, I'm paraphrasing Nancy, with a great sense of humor. In the first year at Stanford, students take standard courses in applied and theoretical stat, and everyone at the University of British Columbia told Nancy that she should work with Brad. So she went to ask him if she could work with him, and he said that he wouldn't be a very good advisor, because if he were interested in the problem, then he would figure it out himself. If he wasn't interested in the problem, he didn't want to meet and talk about it every week. Therefore, Brad encouraged Nancy to talk to Rupert Miller, who had a little drawer in his desk with a stack of file cards. On each card was written a problem. So he just opened the door, the file drawer, and started looking through. Then Rupert handed Nancy this file card that had a problem on it about robust inference for survival data. And he told her how to start as well, because he had a student working on expressing the survival data estimator as a functional, which was the first step towards getting robustness. So that's what Nancy worked on. And they say the rest is history. On behalf of Pfizer, I extend a cerebral and genuine embrace to you, Nancy, in celebrating and honoring you as a recipient at the 30th Distinguished Statistician Colloquium.
Thank you.
Okay, thank you, Dr. Capillari. At this point, we will take a 10-minute break and begin promptly at, is that correct? Is that, okay, about at 4:30, to commence the interview portion of the program. So we'll see you real soon. Thank you.